Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about dominance and Pareto optimality. My name is Rick and my co-teacher who prepared these notes is Christoph. So let's start with an outline of what we want to cover today. We want to talk about payoff matrices, dominance, strict versus weak dominance, a process called iterated elimination of strictly dominated strategies, that's a mouthful, the concept of Pareto improvement, and finally Pareto optimality. Let's start by talking about payoff matrices. I just want to make a point here about how you describe a payoff matrix. So you'll often see something like written as or said to be something like an M by N payoff matrix. For example, you might hear us talk about 2 by 2 matrices. When you see M by N, what that means is that there are two players. Let's say that we call them the row player and the column player. And the row player has M possible strategies available to them. And the column player has N strategies. So that's what makes it possible to write down a payoff matrix. Generally, if the row player has M strategies, we might call those R1 through Rm, and maybe we write R1, R2, down to Rm. And the column player might have N strategies, so that might be C1, C2 to Cn, and that lets us write nice matrix, an M by N matrix. So then we would fill in all these boxes. And that would be the payoff matrix. So just to give you an example, hopefully it's already clear to you, but if we have a 3 by 2 matrix, that means that the first player, who we've been calling the row player, has 3 choices or available strategies, and the second player has 2 choices. So I think that's pretty clear. Something you might want to think about. How would you extend this if we had, for example, 3 players? If you have some ideas about that or questions about that, come talk to us in class. For now, let's move on to our next concept, and that is dominance. And dominance, again, is another solution concept that we'll be talking about. It's a way of reducing the possibilities of all, or the set of all possible outcomes to focus on outcomes that are likely or make sense for rational players to play. So I'll start by giving a little example, and we can see how dominance comes into it with this example. Let's say we have 2 players, and the one player, the row player, has strategies A and B, and the column player, let's say they have strategies alpha and beta. Now let's say in this payoff matrix, the payoffs for the row player are 5, 3, 7, and 6. And the payoffs for the column player are 3, 5, 1, and 0. To begin, I'm going to draw the preference arrows. So I'll make a note of that. The arrows that I'm going to draw here show preferences. So for the row player, you'll see that 5 is better than 3 and 7 is better than 6. So the row player always prefers A over B. Now let's have a look at the column player. For the column player, it's similar. We see that 3 is better than 1, 5 is better than 0, so they always prefer alpha over beta. And that brings us to our definition of dominance. In this example, that should make it clear here. This is our example. In this example, we say that A dominates B, or conversely, we can say that B is dominated by A. And likewise, for the column player, we see that alpha, in this case, dominates beta, or equivalently, beta is dominated by alpha. Be very careful here, especially if your English isn't the best, to be able to distinguish between dominates and is dominated by. Those are opposite concepts. The words look a lot the same, but they mean the exact opposite of each other. In a past year, we had a student that was got the terms flipped, and that presented some problems. So dominates versus dominated by. And that leads us to the definition of dominance. We say that a strategy X dominates Y, or conversely, Y is dominated by X if X is always better than Y. And that means X is preferred to Y for all possible choices of the co-player or co-players if there's more than one. A consequence of that is rational players will never choose a strategy that is dominated by another strategy. Now, I've left out a term here because I want to make a distinction between two things. There's the concept of strict dominance and weak dominance. What we've talked about so far is technically strict dominance. So what I should have done is write in here, and in here, that these refer to strict dominance. So let me insert that. X strictly dominates Y, or Y is strictly dominated by X. And down here, again, I should put in the word strictly. And that's just to distinguish between strict versus weak dominance. The definition of weak dominance is, hold on, before I say that, there's another spot here I need to write up here. I need to say strict dominance. Now I can say what the definition of weak dominance is. We can say that a strategy X weakly dominates another strategy Y, or equivalently, Y is weakly dominated by X if X is always at least as good as Y, and sometimes, but not always, better. If it was always better, then we'd be back to the definition of strict dominance. So between these two different definitions, strict versus weak dominance, we will find that strict dominance is a more useful concept than weak dominance. Okay, next, let's talk about a technique you can use using the concept of dominance. It is called iterated elimination of strictly dominated strategies. Or let's use the acronym IESDS. The idea here is that if a strategy X strictly dominates another strategy Y, then a rational player will never choose Y. So Y is never preferred. And because of that, it can be eliminated from consideration. And that results in a simplified matrix. And the neat thing about that is once you've simplified the matrix, that also shows some strict dominance. And sometimes you can repeat this elimination to further simplify the matrix and essentially solve, in our game theoretic sense of solve, which means reveal the significant or important outcomes. Let me say outcomes or sub-games. And that can be a valuable tool. Let's look at our simple game matrix that we had before. If the row player has payoffs 5, 3, 7, and 6, and the column player with strategies alpha and beta has payoffs 3, 5, 1, and 0, then we can apply this iterated elimination of strictly dominated strategies in two ways. So I'm going to duplicate this matrix, and let's look at it twice. So we already saw earlier up here that A dominates B. So that means that player 1 will never choose B, so we can eliminate B. And that gives us a reduced matrix where it's a 1/2 matrix, which means that the row player will only play one strategy, A, and the column player will still have two strategies, alpha or beta. But if we look at the options for the column player, we see 3 is better than 1. So again, this strategy beta here is dominated by alpha. We no longer have to look down here at all because we've already eliminated the strategy B. So now we know the column player will never choose beta in this simplified game, so we can eliminate that. And that gets us down to a 1/1 matrix, which means that that's the only outcome that's going to occur, or at least when rational players are playing. But there was two ways to look at our dominance in this case, because it wasn't just the case that A dominates B, but we also saw that alpha dominates beta. So if we started with that instead, then we would see that beta is dominated, so it's never played, which leaves us with a 2/1 matrix. And now if we look at A versus B, we see that 5 is better than 3, so the strategy B is dominated by A, and we can eliminate B. So again, that takes us down to a 1/1 matrix. Now you might notice, if you're careful, that this top left outcome, the 5, 3, is also a Nash equilibrium. And that's one of the neat things about this IESDS. Did I say that right? Yeah, IESDS, Iterated Elimination of Strictly Dominated Strategies. That's one of the neat things about it, is that you can apply it and it will never eliminate a Nash equilibrium. Let's look at the corresponding procedure for weakly dominated strategies. So let's say we were trying to use a tool, let's call it IEWDS, which would be iterated elimination of weakly dominated strategies. So the idea there would be maybe we would also allow elimination of weakly dominated strategies. If we did that, we would see that we can't guarantee that Nash equilibrium aren't eliminated. So this technique may eliminate Nash equilibrium. Another weird effect that can occur if in the case of IEWDS is that the final outcome, let's say you're going through this iterated process, the final simplified game, let's call it that, final simplified game, it can depend on the order in which strategies are eliminated. So we could have a result where two people are both applying IEWDS, and they just happen to do it in different orders, eliminating different dominated strategies in different orders, and they would come to different final simplified games or final outcomes if it reduced to one box. And that's a little bit of a weird thing, because then it doesn't tell you that this is the important outcome or these are the important outcomes. You might miss some. Also, the fact that it can eliminate Nash equilibria suggests that it's missing something important. So IEWDS is not so much a useful concept compared to IESDS, where we stick to strictly dominated strategies. It might get us further. We might be able to eliminate more, but we might eliminate too much. Okay, let's move on to the Pareto optima. What it is another solution concept, and it can be useful and reveal some important, interesting aspects of a game. First, we should note that the Nash equilibrium, or equilibria, are not always the outcomes that players would prefer. It's perhaps more useful to think of them as the outcomes that players are trapped in. You see, the Nash equilibria doesn't tell you anything about how to choose a strategy, but rather once you've settled on an outcome, it tells you that you're unlikely to deviate, to unilaterally switch away from that strategy. So there is another concept, and this is just one of many, and that is the Pareto optima, or Pareto optimality. And it rests on a concept that we need to talk about, and that is the Pareto improvement. A Pareto improvement is a change of strategy that raises at least one player's payoff without lowering anyone else's. So the idea there is that none of the players would object to making a Pareto improvement, to change from this outcome to another outcome where everybody is at least as good and somebody is doing better. Now, the Pareto optimum is related to that. Call that the PO. It is the outcome, or any outcome, where it's no longer possible to make further Pareto improvements. So that means that a Pareto optimum is an outcome where every change of strategies results in a lower payoff for at least one player. So once you've reached a Pareto optimum and you tried to move to another outcome, at least one player would object to that move because it would involve a lowering of their payoff. Some important things to think about here. The Pareto optimum takes into account the payoffs of all players. But notice we're not making the mistake here of comparing between players. We're not doing anything where we're trying to add up everybody's utility or payoff and say that it's overall better. No, every player is individually looking at their own payoffs and just comparing them to other possible outcomes. We'll see how it works in a minute. And the other important thing here is that it does not restrict the changes to unilateral ones. So we're not just talking about one player changing their strategy while the other players' strategies are fixed, but rather we can change this whole set of strategies. So all the players could potentially change their strategies together, and we compare the outcomes of any two boxes. So these two things are really quite different than what we saw before when we were looking at the Nash equilibrium. And we'll see that the Pareto optimum can give very different solutions than the Nash equilibrium concept. Okay, let's go through an example and apply some of these concepts. Let's say we're considering a 3x3 payoff matrix. And let's say the strategies are U, M, and D. Those might represent up, middle, and down. And the column player can play L, C, or R, left, center, or right. Let's choose some payoffs. This is prepared, so don't think these are completely random. Okay, so we have a payoff matrix here, and let's set up the task. We want to find the Nash equilibria and the Pareto optima, and we want to go through the process of simplifying by using IESDS. Okay, so let's start by looking at the Nash equilibrium. Let's say we want to find the solutions. The Nash equilibria, let's use our method of looking at preference arrows. So I'm just going to copy this matrix to work with it. And let's fill in our preference arrows. Looking at the row player, they would prefer 80 versus 73 and 80 over 28. 57 is not as good as 63, nor is 35, and 66 is the best of the bunch here. Let's look at the column player. 42 is better than 25, and it's better than 32. 26 isn't as good as 54, and 12 isn't either. And 31 is better than 27, and better than 29. Okay, these are all the preferences. We can find the Nash equilibria by simply looking for boxes where all the arrows point in, basically, because these are the locations where nobody prefers another outcome. I should say unilateral switch. So this does not qualify. There's arrows pointing out. There's an arrow pointing down from this. There's an arrow pointing left here. Over here we have an arrow pointing to the right. Arrow pointing down. Arrow pointing up. Here we have an arrow pointing up. Here. All the arrows are pointing in. So that is a Nash equilibrium. And if we look at our last box, then we see there are arrows pointing out of this box. So in this case, there's only one Nash equilibrium. And the technique we used was to notice that the Nash equilibria, or in this case, equilibrium, doesn't have arrows pointing out. So once you've arrived there, there's no unilateral switch that'll take you out. And what we find then is that the strategy pair DC, or equivalently 6331, is the only Nash equilibrium, or at least it appears to be. Next, let's solve for the Pareto optima, and we'll do that by removing outcomes that allow Pareto improvements. You'll remember from our definition, a Pareto optimum is an outcome where there are no further Pareto improvements. Let's grab our original payoff matrix. Okay, we've got our payoff matrix, and what we need to do is look at each one of these boxes and think about, is there another place on the matrix that's better for at least one person and no worse for anybody else? So we'll just go through them one by one. Let's start at the top left. We have 7325. And if we look at that, we can look just below it and we see 80 and 26. Everybody would prefer 80 and 26 over 73 and 25 because 80 is better than 73 and 26 is better than 25. So we can make a Pareto improvement by moving to the next box down, which means that 7325 is not a Pareto optimum. Let's look at that box 8026 now. Now, one thing to notice is that 80 is the biggest payoff for the row player. All the other red numbers are smaller than 80. So moving away from this 80 will always be worse. So right away we know that it's not possible to make a Pareto improvement. And that is the definition of a Pareto optimum. So this is a Pareto optimum. Continuing on, let's look at 2827. Well, right next door to it, we have another box where both the payoffs are better. So that is a Pareto improvement. This is not an optimum. Starting at the top of the middle center column, we have 5742. Now looking at the boxes that are better than 57. 80 is better, but 26 is worse. 63 is better, but 31 is worse. 66 is better, but 32 is worse. And that's the only one, those are the only ones where it could possibly be a Pareto improvement, but it turns out none of them were. So this also must be a Pareto optimum. Let's look at the middle box. 35, 73, and 25 are already better than that. So this is not a Pareto optimum. 6331. Whoop, I see one up here. Both payoffs are better up here. So that would be an improvement, not a Pareto optimum. Now looking at that box, 6632. Where are other boxes that are better than 66? 73 is, but 25 is worse. 80 is better, 26 is worse. Moving on, there are no other boxes that are better for red and better for blue, so this also is a Pareto optimum. Looking at the next one down, 32. There's lots that are better than 32 here, but what about 54? If you look at all the blue numbers, you'll see they're all smaller than 54. So any change, any move to one of the other box is going to be a lowering of the payoff for the column player, which means we're already at a Pareto optimum because we can't move away from it and keep the column player happy. And finally, 5429, we have to go through and look for something better than that. Oh, here's something. 6632 is better for both players, so that is not a Pareto optimum. There we go. We found 4 Pareto optima in this case, and you'll notice that none of them are the Nash equilibrium, which was 6331, down center. So that's weird. That's actually an interesting concept that we'll talk about more later. Okay, let's do the last thing we wanted to do here, which was using iterated elimination of strictly dominated strategies to simplify this matrix. I'll reproduce the matrix and we can go from there. Let me write this down. We want to simplify the matrix by applying IESDS. Okay, we've got the matrix here, and let's look at what steps we can take to eliminate dominated strategies. Let's write down the steps we can take. So let's start by looking at the row player. So we saw earlier that 80 is better than 73, but on the other hand, 57 is better than 35. So U is not dominated by M. Likewise, U is not dominated by D. How about M? M is better here, but worse than everything else here. So M does not dominate anything. And likewise, M is not dominated by anything because of the 80. So let's continue and look at the strategy D. Is it dominated by either U or M? Well, 28 is worse than 73, but 63 is better than 57. So U doesn't dominate D. Let's look at M versus D. 28 versus 80, but again, 35 versus 63. So D is not dominated by M. So we've established that none of these strategies dominates any other one. So maybe we should look at the column player. Let's look at the left strategy and compare it to the center strategy. So 42 is better than 25, but 26 is better than 12. So L is not dominated by C. Let's compare L to R. 25 versus 32, okay, R is better. 26 versus 54, okay, R is better. 27 versus 29, aha! We see that always L is dominated by R. So L is dominated by R, which means we can eliminate L. And that gives us a reduced matrix. Let's go back to looking at the row player strategies. So now we have 57 versus 35 if we want to compare U to M. 57 versus 35, so U is better there. And 66 versus 32, again, U is better. So M in this simplified matrix is dominated by U. And if you look carefully, you'll also see that M is dominated by D. So M is dominated by U or D. Okay. That means we can eliminate M. And that gives us a further simplified matrix. And maybe what I should do is redraw the matrix, this new simplified matrix. We are left with U and D, and the payoffs are 57, 63, 66, and 54. And we can fill in the rest for the column player. So our last step was to eliminate M for the row player. So let's go back and look at the column player again in this new simplified matrix. So now we see that 42 is better than 32 and 31 is better than 29. So C dominates R. So our next step is to see that R is dominated by C, which means we can eliminate R. And finally, we just have to look at 57 versus 63, and we see that in this simplified matrix, U is dominated by D, which means we can eliminate U. And that reduces the entire 3x3 matrix to a single outcome. The outcome DC, or 6331, is the only outcome left after IESDS. And you'll notice that it's also the Nash equilibrium. That's no accident. As I said before, IESDS will never eliminate a Nash equilibrium. Okay, that's all I wanted to talk about, so let's summarize what we've done today. We talked about the notation M by N payoff matrices. We also talked about strict versus weak dominance. We covered this concept called iterated elimination of strictly dominated strategies. And we talked about Pareto improvements and Pareto optima, which we denote PO. Maybe just before I end, we should just review whether there are any terms here that you should keep in mind. Okay, looking through here, dominance. Strict dominance is a term you should remember. And the two ways of saying it, X strictly dominates Y, or Y is strictly dominated by X. Make sure you have those in your lingo. There's also the concept of weak dominance. X weakly dominates Y, or Y is weakly dominated by X. Those should go in your glossary. IESDS, better remember what that stands for and be able to use it, of course. IEWDS, we're not going to really use because it's not a very useful concept. Pareto optimality, the ideas of Pareto improvement, that's important, so remember that. And the concept of a Pareto optimum, that's important, so put that in your glossary. And it looks like after that we just applied these techniques and we're all done. So that's all for this lecture. Thanks for watching.